Maximum likelihood estimation. Let us say we have an independent and identically distributed IID sample x, which is equals to the set of x to the t, where the t starting from 1 to n. We assume that x to the t are instances drawn from some known probability density family, that is the probability of x conditioning on theta, defined up to parameters theta, such that x to the t is approximately 2 the probability of x conditioning on theta. We want to find the theta that makes sampling x to the t from the probability of x conditioning on theta as likely as possible. Because x to the t are independent, the likelihood of parameter theta given sample x is the product of the likelihoods of the individual points. That is one function of theta conditioning on x, which is by definition equals to the probability of x conditioning on theta, and which is equals to the multiplications of the probability of x to the t conditioning on x, where t starting from 1 to n. So in a maximum likelihood estimation, we are interested in finding theta that makes x the most likely to be drawn. We thus search for theta that maximizes the likelihood, which we denote by 1 of theta conditional on x. We can maximize the log of the likelihood without changing the value where it takes its maxima. Log dot converts the product into a sum and leads to further computational simplification when certain densities are assumed. For example, containing exponents, the log likelihood is defined as L of theta conditional x, which is by definition equals to log 1 of theta conditional x, which is, because previously we know that log of 1 of theta conditional x, where 1 of theta conditional x is the multiplications of a lot of terms. So when we take log, that will be the summations of log of the probability of x to the t conditioning on theta, where the summation is summing for all t starting from 1 to n. And let us now see some distributions that arise in the applications we are interested in. If we have a two-class problem, the distribution we use is Bernoulli. When there are k which is greater than 2 classes, its generalization is the multinomial Gaussian. Normal density is the one most frequently used for modeling class conditional input densities with a numerical input. For these three distributions, we discuss the maximum likelihood estimators, MLE, of their parameters. Bernoulli density. In the Bernoulli distribution, there are two outcomes. An event occurs or it does not. For example, an instance is a positive example of the class, or it is not. The event occurs and the Bernoulli random variable x takes the value 1 with probability p, and the non-occurrence of the event has probability 1 minus t, and this is denoted by x taking the value 0. This is written as p of x is equals to p to the x times 1 minus p to the 1 minus x, and where x is taken, a selection is selected among two values, either 0 or 1. The expected value and variances can be calculated as expectations of x is equals to the summations of x times p of x, where the summation is summing for all x, and that is 1 times p plus 0 times 1 minus p, which is equals to p. And the variance of x is equals to the summations of summing for all x of the following two terms. That is x minus the expectations of x to the square times another term, that is the probability of x, which is equals to p times 1 minus p. And p is the only parameter and given an IID sample x, which is equals to the set of x to the t summing for all in xt starting from 1 to n, where x to the t is selected among 0 or 1, and we want to calculate the estimator p hat. The log likelihood is L of p conditional on x, which is equals to log of the multiplications of p to the x to the t times 1 minus b to the 1 minus x to the t, and the multiplication is by multiplying for t starting from 1 to n. So if we separate the two terms instead of the multiplication, instead of the log function, that we can separate them into two terms. That is, the first term is the summations for all t, summing the x to the t times log p. The second term is by log times log of 1 minus b times n minus the summations of x to the t, summing for all t. So for all n different samples, we just separated that into belongs to x to the t or not belongs to x to the t, and also with their log value. Now p hat that maximizes the log likelihood can be found by solving for the differentiation dl over dp when it becomes 0, and the hat circumflex denotes that it is an estimate. That is, p hat equals to the summations of x to the t summing for index t divided by n. The estimate for p is the ratio of the number of occurrences of the event to the number of experiments. Remembering that if x is a Bernoulli with p, the expectations of x is equals to p, and as expected, the maximum likelihood estimator of the mean is the sample average. Note that the estimate is a function of the sample and is another random variable. We can talk about the distribution of pi hat given different xi sampled from the same p of x. For example, the variance of the distribution of pi hat is expected to decrease as n increases. As the samples get bigger, they and hence their averages get more similar. Multinomial density. Consider the generalization of Bernoulli where instead of two states, the outcome of a random event is one of k mutually exclusively and exhaustively states, for example classes, each of which has a probability of occurring pi with the summations of pi summing with index I starting from 1 to k, which is equals to 1. Let x1, x2, and so on to xk are the indicator variables where xi is 1 if the outcome is state I and 0 otherwise. Now the probability of x1, x2, x3 until xk is equals to the multiplications of pi to the xi, where the multiplication is for multiplying I starting from 1 to k. Now let us say we do n such independent experiments with the outcomes x equals to the set x to the t, where t starting from 1 to n, where xi to the t is equals to 1 if experiment t chooses state I and 0 otherwise, with the summations of xi to the t summing for index I equals to 1. The MLE, maximum likelihood estimation of pi is pi hat equals to the summations of xi to the t summing for index t divided by n. The estimate for the probability of state I is the ratio of experiments with the outcome of state I to the total number of experiments. There are two ways one can get this. If xi are 0, 1, then they can be thought of as k separate Bernoulli experiments, or one can explicitly write the log likelihood and find pi that maximize it, subject to the condition that the summations of pi summing for index I is equals to 1. Next, we will discuss the Gaussian normal density. X is a Gaussian or normal distributed with mean expectations of x equals to mu and a variance var of x is equals to rho square, denoted as n of mu rho square. If its density function is p of x equals to 1 divided by the square root of the 2 pi times rho times the expectations of minus of x minus mu square divided by 2 rho square, and where x is between the minus infinity and the positive infinity. Given the sample x equals to x, the set of x to the t, where t starting from 1 to n with x to the t, which is approximately by the Gaussian normal distribution n of mu rho square, the log likelihood is L of mu rho conditional x, which is equals to minus n divided by 2 times log of 2 pi minus n times log of rho minus the summations of x to the t minus rho, mu to the square, summing for all index t, divided by 2 rho square. The MLE that we find by taking the partial derivatives of the log likelihood and setting them equal to 0 are the following. N is equal to the summations of x to the summing for index t divided by n, and s squared is equal to the summations of x to the t minus m, the average that we have discussed before, to the square, then when we're summing for all index t divided by n. We follow the usual convention and use Greek letters for the population parameters and Roman letters for their estimates for the sample. Sometimes the hat is used to denote the estimator, for example, mu hat.